From our last lesson, if we had this trinomial where a was equal to 1, we were able to factor it really quickly by just finding our magic numbers. Now let's look at 4 times 3 equals 12, and 4 plus 3 equals 7. So there's our magic numbers. Now look at this question here. It's similar, but the exponents are different. Our first one has an exponent of 6, and our second one has an exponent of 3. Now let's go about this the long way at first, by decomposition, and then we can look for a pattern to hopefully save us some time. Our a times c equals 12. 1 times 12 is 12. And two numbers that add to be 7 is 4 and 3. Now remember with decomposition, we always had to leave our first term the same, and then we decomposed our second term. The exponent on the x stays the same. It'll stay the same there. Just get that 3 in there so it's more clear. And then 3x3 plus 12. We leave our last term the same. So 4x cubed plus 3x cubed equals 7x cubed. Value still the same. Now we factor by grouping is our next step in decomposition. And there's 3 x's common to both terms. So if there were 6 in the first and we factor 3 out, there's only 3 left. And then that 4 is still there, but there's no x's remaining in that term because there was 3, but we factored them all out. Now in our last two terms, we can factor out 3, but that's it because there's no x with the 12. So we're left with x cubed plus 4. And as usual, our binomial is the same, so we can now factor that out, x plus 4. So when I factor the x plus 4 out, I'm left with x cubed, plus 3. And that is done. Now let's look to see how similar it is to our question up above. It's just that the exponents are different. And as I say that, I realize that I lost my 3 along the way there, and I've got to be sure that that is there. So when you're factoring questions that have larger exponents, the first one being 6, the second exponent being 3, as long as the first one is double the second's, then you can still use your magic numbers and not have to go through decomposition the whole time. So let's move the screen down so we can see the next example. So rather than doing decomposition for our x to the power of 10 plus 11 to the power of 5 plus 24, we can realize that as long as the 10 is twice as big as the 5, we can still do this by factoring trinomials. We're just going to have our exponent of 5 now. Our magic numbers would be 8 and 3. Again, that has to have the exponent of 5. So 8 times 3 equals 24, which is the same as the c term, and those 8 plus 3, when you add them together, equals 11. So that's factored now without having to do decomposition, and it's fully factored. We don't have to go any further. Here's another pattern we can look at. We're going to go, again, the long way first by decomposition, and then we'll go look to see if we can find a pattern to do it a little bit faster. So when we're doing decomposition here, we leave our first term the same, and then we decompose our second term. So we know that 5 times 2 equals 10, and 5 plus 2 equals 7. So our letters stay the same. We're just sort of breaking it apart. 5 plus 2 is still equal to 7. And then we write our last term the same with decomposition. Those steps never change. Now we can factor by grouping. So there's 1x common in both of my first terms. So I'm left with 1x plus 5y. And in my second term, I can factor out 2y. That's common in both. So I'm left with x plus 5y. And as always, if done correctly, our binomials are the same. So I'm going to factor out x plus 5y. And that will leave me with x plus 2y. Now look, it's very similar to just putting in magic numbers, except for now we have a y on the end to account for the y squared that's attached in the third term. Now let's solve this example here. Now that we know our patterns, we don't have to go through decomposition anymore. So we can just find our magic numbers that work. -4 times -5 equals 20, and -4 plus -5 equals -9. Now when we have that y squared on the end, we have to remember to put it on the end there as well, half of the exponent. So x minus 5 was our other magic number, y to the power of 1. So this pattern here, we can see we can use trinomials, and we just take our exponent and divide it by 2. So our exponent there is going to be x to the power of 4. We can put in our magic numbers, and then remember that we have to put in half of the y value of that last term. So that last term is 20, so we have y to the power of 10. 6 times 2 equals 12, and 6 plus 2 equals 8. I'll just make that a little bit neater there. Let me just clean that up. And that question there is now fully factored. Now let's look at a difference of squares. Our first one should be pretty straightforward for us. We can square root the first term, square root the second term, and then we just write it again with the opposite sign, with addition now. This next question is really similar, but realize that the exponent is now 4. So when you're doing difference of squares, again, you just half your exponent. So we have x squared minus 3, x squared plus 3. It's always a good idea to check to see whether you've factored fully, if there's anything else you can do to those binomials to factor it further, but we can't, so we're all done there. Now in this example, x to the power of 4 square rooted is x squared minus 4. And we write it again, the opposite sign, x squared plus 4. When I stop to see if I can factor this further, I realize I can. My x squared minus 4 is still a difference of squares. So I can square root my first term and square root my second term. Then I write it again with addition. And I can't forget that binomial that I haven't touched, that x squared plus 4. That's not a difference of squares because it's an addition sign separating the two. So that question there is now factored fully. So let's look at our last one. We'll just pull it out a little bit. We can square root the first term by taking the exponent in half. The square root of 4 is 2, and the square root of 16 is 8. I wrote that a little bit big, but we can still get it in. Rewrite it again with the opposite sign. And that is the last of our factoring examples.